All right, so what I'm going to do in this video is I'm going to work through this worksheet and try to explain the best that I can what I'm doing and why I'm doing it. So this worksheet starts with a mono-hybrid cross. It starts out with a parent generation. So in terms of generations, they go parent, first filial, second filial. When you're talking about generations, the square for the parent generation is the F1 generation, and the square that comes out from crossing the F1 generation is the F2 generation. So for example, in this question it says, if you crossed the offspring in the F1 generation above, so that means I've already crossed these parents, which the only possible outcome for this cross is this. So when it asks you to do the cross for the F1 generation, they're saying cross the two heterozygous individuals. So it's saying do this cross. And this cross is your standard F1 monohybrid cross, which I get my big D, big D, big D, little d, big D, little d, and then little d, little d. So the phenotypic ratio is 3:1, which is what they're asking for. 3 would be expressing the dominant trait, and 1 would be expressing the recessive trait. So for example, if big D is the gene that codes for the protein to make brown hair, the ones in the yellow would have brown hair, and the ones with the two little d's might have something like blonde hair. So phenotypic is the physical trait, so the physical trait are what we're talking about, not the genotype, the phenotype. Okay, dihybrid cross. In this case, when we go to make the square, we have to FOIL. So I would FOIL first. You FOIL each parent to determine the gametes, or the sperm or egg, that they would pass on. So in this case, they're both the same. So red is big G, big T. Sorry, let me fix that. I did that with a blue, like that. Make this nice and color coordinated for you. And then this one for both. Now I'm only putting them on each side because the parents are the same. And then inside is green. And outside is orange, which is my two little ones. And now I'm going to do some speed punneting. I shouldn't do it in blue. A little too much speed, huh? There we go. And I'm trying to take... Oh, man. Poop. I'm trying to take and keep the capital letters first, right? And we're trying to keep it in alphabetical order. G comes before T in the alphabet. And now I'm going to highlight them based on their phenotype. So the phenotype, the ones that are all expressing the dominant traits, are going to be found in this triangle shape. If you did the gametes the way I did, the ones with at least one recessive or two recessive T's, these all have one recessive trait, which is the T's. They're both lowercase. Here's my recessive G's, and down here is my double recessive. So it says, what is the phenotypic ratio for the dihybrid cross above? Well, you should memorize that if I do a dihybrid cross with two parents that look like that, it's always 9 to 3 to 3 to 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9 to 3, 1, 2, 3 to 3, 1, 2, 3 to 1. And that's how you get that ratio. The ones that look different is the phenotype. Then we get a probability problem. It says, what is the probability of getting the offspring? So this is what we're looking for, okay, from a mother with the genotype. So I have one genotype. So what it's saying is you're crossing a parent that looks like this with another parent that looks like this. When you write letters that look the same lowercase and uppercase, you put a little line over the top, right? That shows you that that's lowercase. It's just a good way to notate so you don't make mistakes, right? We don't want to make mistakes. Okay, so how I'm going to do this is I really like to split them out. Like so. And I'm going to do separate boxes. So I'm going to start off with A. So I'm going to take this parent, and I'm going to take this parent, and I'm going to do a normal little Punnett square. And then what you do is you look at the offspring. So I look up top here, and I say to myself, they want the offspring to have a heterozygous big A, little a. What are my chances of that with these two parents? Well, 2 out of 4, or 1/2. So that means I'm going to write 1/2. And now I move on to the next one. So I grab my B's. Now you don't even have to do these squares if you can visualize what's going to happen. I mean, I know this is going to look just like the other square. But now they're asking for little b up here. So that means this one, instead of being a half, is 1 out of 4. So it's a quarter. And you continue doing that with the parents until you get, oh, that's terrible. Even though there's a line over them, I want them to look somewhat smaller. Okay, so this one's tough. Obviously, there's a line over that one there. So this is 50-50. So this is still a half because we're looking for little c, little c. So this is still a half. These are little c's. And now we're looking for heterozygous, and we're crossing these d's. So I have this times this. Remember, I'm just grabbing them from the parents. Still 50-50, right? This is that one. And now the E's, it's 50-50 again. It's that cross. And it's looking for the double recessive, which is going to be this side. It's a half. So a half times a fourth is an eighth. An eighth times a half is a 16th. 16th times a half is a 32nd. And a 32nd times a half makes it 1/64. That is the answer. The next problem. This one is somewhat of a trick because you don't have to do what I just did in problem number 3 because it's only asking you for one thing. It says they want a child who has their brown hair, which is dominant. And it says, what is the probability that Amadeus and Hermione will get a child with brown hair if their genotypes are this? So when you set this up, you only have to do the B's because that is the only gene that codes for brown hair in this case. And only this one's not brown hair. So it's 3/4, or there's a 75% chance. All right, on to blood types. So I always like to write the genotypes for each one out first. So I'm going to try to zoom in here. Let's see. B type. I always do that. AB type O. The genotypes, A's can be heterozygous. B's can be heterozygous. AB is a codominant situation. They express both. And O is the double recessive. So it's a man with type AB blood, so that's easy enough. AB. There's not multiple options for that one. There's only one option. And a woman with type O, there's only one option there. I don't know what I was doing there. So I just have to do a little square for this one. And there you go. So what type of blood can they have? Well, these are both type A and type B. These ones are A, these ones are B. They're heterozygous for it, but they're A and B. All right, next problem. This one adds in RH factor. RH factor is that positive and negative. You either can have positive, 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 negative. You can have negative. Phenotype-wise, these ones would both be called positive. The negative is the double recessive. Sorry, a little bell action there. So the first thing you have to think about is really it's a process of elimination. And if you look at the children and the parents, you can figure out that there's specific genotypes that have to be true in order to have specific offspring. So let me give you an example. The mother is type A. It says a woman who has type A blood. Now, if we start with her, we might be like, well, I don't know whether she is homozygous for type A blood or if she is heterozygous for type A. And we have the same problem with positive. We don't know whether she's homozygous or, I'll just leave that like that, or heterozygous. So she's positive, positive, or positive, negative. If I look at the word problem, the first thing that right away makes us figure out what she is it says she has a daughter who is type O. If she has a daughter who is type O, she has to be heterozygous. And I'm jumping ahead, but I'll give you a reason why. If she wasn't, like let's say she was homozygous for A, and even if the father was O, all of her children would be A because O is recessive. So that means in order for her to have an O child, she has to carry at least the one O, even if the other parent is also heterozygous. Because in this case, this bottom corner would be O. So we know the mother is heterozygous. She also has a son who is negative. It's the same concept of it as I just explained. In order for them to have a negative, she has to be heterozygous. So the mother, which is here, the mother has to be type A with a recessive O, so heterozygous, and she has an RH factor of plus minus. So you would say she is type A positive, which is what it tells us she is. We just didn't know that this was there and that this was there without knowing her offspring. So once I know that the mother is carrying a recessive O and a recessive I, and then I look forward and I can see the son is negative, then I am able to figure out that, well, if he's B, he has to be IB little I. And the reason why is if the mother gave him the A, he would be A. If the mother gave him the A and the father gave him the B, he would be AB. So the mother didn't give him this one. She gave him that one. And the father gave him this one. So he's going to be IB and then little I or O. And then he's negative, which is the homozygous recessive version of RH factor. So that's his genotype. And I kind of just said, well, since the father isn't listed, but we see the daughter is O, we know he at least has one O gene. And then the son is B, so we know he has a B gene. And then the daughter is positive, and the son is negative, so we know he at least has a negative. And we know he has possibly a positive. Okay, so he could be IB little I plus minus, or, I mean, technically, he could also be negative, negative. And that's because if he is negative, negative, and the mom is negative, positive, there's still the opportunity to, like a 50-50 shot, half their kids will be negative, and half them will be positive. So these are the possible answers for the father. When you get to number 9, that starts incomplete dominance, which is listed right in the first sentence there. The trait for type of hair is incompletely dominant. A man with wavy hair reproduces with a woman with wavy hair. So the heterozygous genotype leads to a new phenotype, which messes up your ratios. So what I mean by that is that in a typical monohybrid cross, you would say that these 3 have the same phenotype. But with an incompletely dominant, that's not the case. So these 2 are wavy. This one here is straight hair. And this one here is curly. So when it says, what is the probability that their child will have wavy hair? 2 out of 4, or 1/2, which is 50%. If you were going to do the phenotypic ratio for this, it would be 1 to 2 to 1, which is different than a typical monohybrid cross, because now I have 1 straight hair, 2 wavy, and 1 curly. So a little bit different. It doesn't follow that 3-to-1 pattern, making it a slightly different problem. So finally, to the last problem on this worksheet. This one is a chi-squared problem. And we're doing a dihybrid cross, so what it's expecting you to understand in the first place is that if I'm doing a dihybrid cross, my expected outcome is 9331. You have to know that in order to do this problem, because it's going to ask you to base your comparison in the population that comes out in this problem to what you would expect, and that's the whole point of this test, right? So we have a dihybrid cross of plants, and we get the following data, and it writes out the data for me, and it gives me the phenotypes, and then I have to create this chart. This is a chi-square chart. So in this box, I'm going to put the phenotypes, which the first one is purple tall. The second one is white tall, purple short, white short. So I'll just try to keep that at the top there. White tall, purple short, white short. Okay. The observed is whatever we observed. So 245, 73, 96, 41. The expected is this whole idea of 9, 3, 3, 1. So something that I have to do first is I have to total the population. So 245 plus 73 plus 96 plus 41. 9/16 of the population to be purple and tall. I like to do 9 divided by 16 first, so that gives me 0.5625. And I have to take that number and multiply it by the total population. So times 455 equals 255.9375. And we will adjust these numbers later to make sure that we have nice whole numbers, because you can't have a part of an individual. I would expect 3/16 of the population to be white and tall, and another 3/16 of the population to be purple and short. 3 divided by 16 gives me 0.1875 times the total population, which gets me 85.3125. So they're both the same chances, so we use that number for both of those. And then the last one is 1/16 of the population would be white and short. So 1/16 is equal to 0.0625 times 455 equals. Now, if you have a fancy calculator, you can clearly just put in fractions and all that good stuff. They even have this chi-squared somewhere in your calculator. But so now this goes under the expected. So I have 255.9375. I have 85.3125, 85.3125, and 28.4375. What I always do is I want this to equal 455. So I'm just going to adjust. This is probably frowned upon, but this is how I do it. I'm going to adjust these so that it works. So I'm going to take this 28 and this 255, and I'm going to make it 256, and I'm going to make it 29, because that's 170, 199. Yeah. So I want it to be 455. Now I have to go through this process of plugging it into this equation. And what I'm going to have to do is I'm going to have to sum them all up to get my chi-squared value. So, for example, I go observed minus expected, so it'd be 245 minus 256 squared divided by expected 256 equals. And I do this all the way down here. Sorry. And 41. Change it to 29 equals. And I plug that into my calculator and I do all the math. Once I have all my numbers, once I have all my values, I would sum them up and get the total, which comes out to 8.55. So I'm going to use that value to determine whether this is coming out within the expected range or if there's a significant difference. So what I do is first I have to find degrees of freedom. The degrees of freedom equals n minus 1, which is the number of outcomes, minus 1. We have 4 possible outcomes of phenotypes. So our degrees of freedom equals 3. So I go up to my chart, and I'm in this row. And typically, we look at a p-value of 0.05. And what value we're looking at, this critical value, is 7.82. If our value is greater than 7.82, then we have a significant value here, meaning that this population and this ratio of each individual of these phenotypes that we observed is not following the expected 9-3-3-1 pattern. So most likely this is a non-Mendelian case. So in this case, we're asked you on 13, does your collected data differ significantly from the expected values? Yes. 8.55 is greater than the critical value of 7.82. So yes, this is significant. So we would think that this is some sort of non-Mendelian inheritance. It doesn't follow Mendel's laws. The law of segregation or the law of independent assortment is somehow being affected. So one more thing I want to cover before I wrap chi-squared up is sometimes they will ask you is, should you reject the null hypothesis? In this case, the null hypothesis is that there is no significant difference between the observed and expected ratios predicted by Mendelian inheritance laws, which these laws, again, law of segregation and the law of independent assortment. So in our problem above, should we reject? Yes, we should reject. And we would reject because our value is greater than the critical value. Once again, this one. So we would reject because it's not following the laws of Mendel. So these are not being followed. So we would reject the null hypothesis. The null hypothesis being that there's no significant difference between the observed and expected. Or in our case, did it follow a 9331? Well, based on our chi-value, our chi-square value, no, it didn't. So we have to reject the null hypothesis.